In the last physics video, I walked through basically all of the equations on our equation sheet, and we went over a part called electromagnetism in mirrors, which is pretty much all of our eye diseases and optics and contacts and like focal points and all of this stuff. And I thought I would just kind of go into a deeper dive of all of that terminology and all of how that works. So we're going to start off with reflection, angle of incidence, all of those equations, and then we're going to move down to mirrors and then also move down to lenses, which are very similar. So let's get started. So when we talk about angle of incidence and angle of reflection and all of that, we're usually talking about a light ray coming in and it being, some of it being reflected and some of it passing through the medium. So you can think about when light is shining down on water, you have that angle of refraction. If you've ever noticed that the light is a little shifted in the water versus in the air. Let's say this is the light first coming and hitting the surface. And I'm gonna draw a just perpendicular line to the surface down the middle, and this angle here, theta 1, is going to be our angle of incidence. Now some of it is going to be reflected, so it's going to come up this way, and then some of it is actually going to travel into the medium, so that's going to look like this. Now this angle here we'll call theta 2. Theta 2 is going to be our angle of reflection. Pretty self-explanatory here. Just remember that we are measuring it against the line that is normal to the surface. We're not measuring it against the surface itself to get those angles. Now this one down here, if you could have guessed, is going to be the angle of refraction. And we can go ahead and label our rays. So this is going to be the incident ray, this is going to be the reflected ray, and this is going to be the refracted ray. All right. And if we're talking about the mediums, we can call this medium up here N1. Let's say this is air or something like that. And then this medium down here is going to be N2. So in our picture that we have a surface that is going to be the boundary between like air and water. So N1 and N2. We have a light ray that's coming in at an incident, and some of it is being reflected and some of it is traveling through the medium. Now we can kind of talk about the equations and the relationships between all of these variables. So first, the relationship between these mediums is going to be the speed of light over the velocity of the ray. And that's not something that you can kind of change with the depth or the length or anything. It is a constant property. Now talking about the angles of incidence, we have N1 sine theta 1 equals N2 sine theta 3. So it's saying that the value of n for the first medium times the sine of the angle of incidence is going to be the same as the value of n for the second medium times the sine of the value of refraction. So remember that this is theta 3, not theta 2. So this is not the reflected ray, this is the refracted ray actually going into the medium. So that's everything for angles, reflection, refraction, how they fit in with each other, different mediums, stuff like that. Now we're going to move on to mirrors. So we're going to do concave and convex mirrors really quick. So for concave, let's say we have a ray coming in and hitting this mirror like this. It is going to reflect like this, and it's going to go through something called the focal point. And I'm going to draw another dot out here that is going to be for our center of curvature. So the center of curvature is basically just the center. If this mirror was a circle, the center of curvature would be the center point. So the distance between the center of curvature and the actual lens is going to be the radius. So something important about concave lenses is that they are real images and they are inverted. And the way we can kind of think about this is if we have a concave mirror here, the light is coming in, the focal point is in front of the mirror. So it's at a spot that is like truly real in space. So the focal point is where all of those lights coming into the mirror converge. So if we had multiple light rays coming into this mirror, they would all be reflected and they would all converge at the focal point. That's what the focal point is caused. And since they're all converging at a space that is real in time in front of the mirror, between me and the mirror, the image that is going to be formed is going to be real. Now the image doesn't necessarily form at the focal point, it can, but we'll talk about an equation in a second that shows where you can derive the distance of the image and the object is based on the focal point. So now let's move over to convex lenses, and then hopefully this real and inverted images would make a little bit more sense. So let's say we have an incident ray coming in here, and it's going to pass straight through the convex mirror like this. It's not going to be reflected because it's flipped the other way. Now the focal point is going to be here. This is going to be where all of the rays converge. So if you have multiple rays coming into this mirror, they're all going to converge at that red focal point. And then again, our center of curvature is going to be on the inside. In convex lenses, these are going to be virtual images, but they're going to be upright. And this means that if you have a concave or convex mirror here and light is coming in this way, the focal point is somewhere behind the mirror. So that's not somewhere that's real in space. So where all the light converges is somewhere arbitrary. So that's going to make it a virtual image because the focal point is not somewhere in real space between me and the mirror. It's somewhere behind it in the mirror. Now, if we want to talk about getting the distance from where the image actually forms, we can use the equation 1 over O plus 1 over I equals 1 over F. This is saying that 1 over the distance of where the object is times 1 over the distance of where the image forms is the same as 1 over the focal point. And so these are distances. So I'll say object distance, distance. And focal point is also a measure of distance. Focal point is just the distance between the actual mirror and then where the focal point actually is. So this equation is how you can tell where an image actually forms, or if you're given the distance of where the image forms and the focal point, you can figure out where the object actually is. We can also talk about magnification. So that's M, and that is equal to negative the relationship over where the image is versus where the object is. And this should make sense because if the image is getting larger while the object is staying the same, it's obviously getting multiplied, is getting magnified. So I'll put magnification. Okay, and that's it for mirrors. Now really quickly, to make it more pathology based, we're gonna go to lenses. So we're talking about contact lenses here normally, or glasses, lenses, stuff like that. We have diverging and converging lenses, and they're gonna look fairly similar to the mirrors that we just talked about. And the light rays are going to look very similar, but the images that are produced are going to be different. So whether they're virtual or real images are going to be different. We'll talk about that. So we have diverging lenses and we have converging lenses like this. Okay, let's start with diverging. So with diverging lenses, if you have rays coming in, they are going to go every which way. And this is why it's called diverging, because it spreads out those light rays. Now, where they actually converge is going to be somewhere over here. So this is all the reflected light. And this is going to be used in cases of myopia, which is nearsightedness. Now, this is a negative focal point, which is different from the mirror because the light is actually going through the lens. So the lens is a clear material. The sign conventions are going to be different. So we can think of this one as virtual because the light rays are never technically, as you can see, they're passing through the lens. Only these dotted lines that we drew that are the reflected different rays are what converge, so that's what makes it virtual. So in this sign convention for lenses, the focal point is going to be negative. And I know it's confusing because the focal point on this mirror is positive because the sign convention is different. Now let's talk about converging lenses. Maybe it'll make a little bit more sense once we have both. So converging lenses, we have light rays coming in like this, and they're all actually going to truly pass through this point. So again, we can kind of see why it gets its name, converging lenses. All of these light rays are converging into this one point, and this one point is real. So we have to remember that lenses are different from mirrors. They're not being completely reflected, they're passing through. And so when they're passing through and they're actually converging at a space that is real behind the lens, it's going to be a real image. So this is a positive lens. The focal point is positive and it's a real image. And this kind of lens is used to treat hyperopia, which is farsightedness. Let's zoom out and kind of talk through it. So for lenses, diverging, the light rays when they pass through the lens are diverging. They're not coming to a point to form a real image. They're all going opposite ways. They're being dispersed, diverge. Okay, and so the sign convention of lenses, a focal point that is in between where the light is coming from and the actual lens here is going to be negative. And you can think of this as producing a virtual image because as we can see by these dotted lines we drew, the light rays are never actually converging. Since the rays never physically converge, the image that's formed is virtual. So that is a way to think about that. And then also just to remember that this is a type of lens that we use in glasses to treat nearsightedness. And I remember this by thinking nearsightedness, the lights converge near to you. So nearsightedness, where converging farsightedness, the lights converge far from you. That's a way of thinking of it. But now converging lenses, these are positive lenses because by the sign convention that we mentioned earlier, the focal point is positive. So when the light goes through this converging lens, they're actually physically meeting behind the lens. Now, it's not like mirrors where this focal point behind the mirror is somewhere random inside the mirror, not actually real. This is a lens, so this is different. So it's actually passing through the lens and is actually converging at a real point in space. So that's why it's positive, and that's why it produces a real image. Mirrors, again, a little bit different because mirrors completely reflect back all the light. So like in convex mirrors, this focal point is going to produce a virtual image because there's really nothing actually behind the mirror. The focal point being behind it means it's a virtual image, where as concave, the focal point being in front of it means that it's a real image because that is a real point in space. A little confusing, it'll take a little bit to get used to, but that is all I have for you for lenses, light rays, angles of incidence, reflection, focal points, all that good stuff. All of the notes from this video will be on the link tree. It'll be under physics and then optics. So hopefully now that section of the physics equations make a little bit more sense. You're more comfortable with the variables. It'll take some getting used to. Memorizing the difference between mirrors and lenses are a little bit confusing, but that is all I have for you today.